Hello, IM3 STEM. As we have just completed testing in Unit 4, we're now ready to go into Unit 5 and work in Chapter 6 of our book. So the first lesson, 6.1, is called Angles and Their Measure. I thought I'd start here by just reading this paragraph because I feel like it's really well written and it really talks about the answer to the question why study angles in trigonometry the way that we do. So here we go. Angles. As derived from the Greek language, the word trigonometry means measurement of triangles. Initially, trigonometry dealt with relationships among the sides and angles of triangles and was used in the development of astronomy, navigation, and surveying. With the development of calculus and the physical sciences in the 17th century, a different perspective arose, one that viewed the classic trigonometric relationships as functions with the set of real numbers as their domains. Consequently, the applications of trigonometry expanded to include a vast number of physical phenomena involving rotations and vibrations. These phenomena include sound waves, light rays, planetary orbits, vibrating strings, pendulums, and orbits of atomic particles. The approach in this text incorporates both perspectives, starting with angles and their measure. So here we are with lesson 6.1, angles and their measures. We've gotten into talking about angles, and so now as we get into just getting into details of angles, an angle is determined by rotating a ray about its endpoint. The starting position of the ray is the initial side of the angle, and the position after the rotation is the terminal side, as shown in the figure to the left. The endpoint of the ray is the vertex of the angle. This perception of an angle fits a coordinate system in which the origin is the vertex and the initial side coincides with the positive x-axis. When an angle is in this position, that's called the standard position. So with that said, when we start with the angle forming at the x-angle, if we go in the counterclockwise direction, we're talking about a positive angle. So you can see that happening from this position right here where it says positive angle, and we're rising up from the positive axis. So if we go from the positive x-axis and head in the clockwise direction, then that's called a negative angle. Angles that are labeled with Greek letters A, B, alpha, beta, and theta have the same initial and terminal sides. So such angles are referred to as coterminal. So if you look at the way that they're denoting these angles with arcs, you see we're starting once again from the positive x-axis and forming the angle alpha. But since it ends in the same place as the negative angle beta, those are two angles that are said to be coterminal. Likewise, in the picture on the right here, you'll see that we're rising from the positive x-axis and forming angle alpha. But note that that is coterminal with an angle that was formed starting at the same place, rotating all the way around and passing through that positive x-axis and continuing and ending at the same place, making it coterminal with the angle alpha. So when we talk about measures of angles, we typically talk about degree measures of angles as determined by the amount of rotation from the initial side to the terminal side. So the most common unit of angle measure is the degree. And you guys know this mostly because of things like riding a skateboard and doing tricks on a skateboard that involve rotations. And so here's where you probably have the best idea or the most common idea of what a 360 is, which is a full circle rotation, versus completely changing direction exactly halfway, which would be 180 degrees. And then all those angles in between. So take a look at some of these. They've labeled, as we get into talking about some of these things, we've got 90 degrees, which is 1/4 of 360, and 60 degrees, which is 1/6 of 360, 45 degrees, which is 1/8 of 360, 30, which is 1/12 of 360. And just that's just noting these angles as fractional parts of the entire circle, as we focus just on quadrant 1. So as we mention quadrant 1, notice we're talking about Roman numeral 1, Roman numeral 2, 3, and 4 as quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So notice in quadrant 1, we're talking about 0 to 90 degrees. And then as we go from 90 degrees to 180 degrees, we're referring to now angles that are in quadrant 2. Quadrant 3 has the angles 180 degrees to 270 degrees. And then quadrant 4 have angles all from 270 to 360 degrees. The thing to note here too is that notice the angle 90 degrees is not in quadrant 1 nor is it quadrant 2. And likewise with 180, that's not in quadrant 2 nor in quadrant 3. 270 is not in quadrant 3 nor quadrant 4. And 360, or one full circle, is not in quadrant 4 nor is it in quadrant 1. We call those angles quadrantial angles, and that they are just not listed as belonging to any one quadrant. So as we continue to categorize angles, let's remember some of the definitions that we have here. If we have something called an acute angle, now we're talking about an angle that's measuring greater than 0 degrees and less than 90 degrees. That's called acute. A right angle is a quadrantial angle, and it is 90 degrees. And an obtuse angle would be something that is greater than 90 degrees but less than 180 degrees. As we fold over to the other side, then we still start using the terms obtuse and acute. 180 degrees is what's called a straight angle. It's a half revolution. And then one full revolution, of course, is 360 degrees. So here in example 1, we're talking about sketching and finding coterminal angles. So let's take a look at this. For the positive angle 390, we could subtract 360 to obtain a coterminal angle of 30 degrees. So here that's listed in this figure right here. And take a look, there's 390 is starting at the positive x-axis, swinging all the way around, and then going beyond 30 degrees. Well, that angle is beyond one full revolution, but it is coterminal with 30 degrees. If we talk about the positive angle 135, we could actually subtract 360 degrees to obtain a coterminal angle of negative 225. So that's depicted in this picture right here. Notice I can go from the positive x-axis, and I can travel beyond 90 degrees and talk about 135 degrees. So there's 135 degrees, but that can also be spoken the same as, if I subtract from 360, I'm really going a negative 225 degrees. And notice too, I can even say 135 minus 360 degrees. That gets me my negative 225. And so that works just fine there. For a negative angle, negative 120, I can add 360 to that, and I can turn that into 240 degrees. So let's take a look at that figure right here. We're starting once again at the positive x-axis. We can go 240 degrees, which is beyond 180, and going an additional 60 degrees to form 240 degrees. If I take that angle and subtract 360 from 240, then I end up with negative 120 degrees, which starts at the positive x-axis but heads in the clockwise direction to that same coterminal side. So you should remember too that there are these descriptions of things called complementary and supplementary. Complementary angles are those that add to 90 degrees. So alpha plus beta, if I add those together, I get 90 degrees. That makes alpha the complement of beta, and that makes beta the complement of alpha. Similarly, we can talk about supplementary, and the big difference is for supplementary is that two angles now that add to 180 degrees are called supplementary angles. And so in this picture right here, you see that alpha, when I add it to beta, makes 180 degrees, and so that makes alpha the supplement to beta, and beta the supplement is to alpha. So let's look at example 2 here. We're talking about complementary and supplementary angles, and it says, if possible, find the complement and the supplement of 72 degrees and 148. Well, let's talk about 72 degrees first and talk about its complement. Well, the complement is found by taking 90 degrees and subtracting 72 degrees, which is going to give me 18 degrees. And so 90 minus 72 gives me 18 degrees, and so 72 degrees and 18 degrees are said to be complementary. Complements. Okay? The supplement of 172, we can find that by subtracting 72 from 180. So 180 minus 72 gives me 108 degrees. So that makes 108, 72. They are supplements. Okay, so now they also talked about not 72, but also 148. Because 148 is greater than 90, there is no complement to 148. But the supplement would be found by taking 180, and I could subtract 148, and I would get 32. So 32 degrees and 148 degrees, those are supplementary. Okay? So there that is for example 2. Okay, we're in the season for this, so here goes. What do you get if you divide a pumpkin's circumference by its diameter? You get pumpkin pie. All right, so this is what we're really talking about. We're talking about where does pi, the number, come from? Well, the pi number is created by this definition right here, that if we take any circle and we talk about how far around the circle, we call that the circumference, and we also talk about how far across the circle and call that the diameter. So if this is the center of the circle, then the diameter is this distance right here. But notice that that's also, because that's the center, two r's. So we can say diameter, but we can also say that again and call that pi is equal to the circumference divided by 2r. Now, if we take that 2r and multiply both sides by 2r, then we get that the circumference of a circle then is 2 pi r, And that's what we talk about with the circumference of a circle. And so that is, notice, the entire length around a circle. So that brings us to then this idea of something called radian measure. Radian measure, the definition goes like this. 1 radian is the measure of a central angle, theta, that intercepts the arc S equal in length to the radius r of the circle. You hear that? So r is the same length as S. In other words, if I took r and called it a piece of string and laid it right on top of this edge of the circle, when I got to the length of r by doing that, I would make this arc S. So that makes the measure of the angle then what's called a radian. It's the length of a radius of the circle overlaid on top of the edge of the circle. So let's talk about how that looks this way. So because the circumference of a circle is 2 pi r units, it follows then that a central angle of 1 full revolution corresponds to an arc length of S being 2 pi r. Moreover, because 2 pi is about 6.28, there are just over 6 radius lengths in a full circle shown in the figure. So that means that I could go 1 radius, 2 radius, 3 radius, 4, 5, 6 radiuses, and then there's this little gap right here. And in that little gap, that's going to be how much radians? Well, about 0.28 radians. And so that really kind of confirms the whole idea that since pi is 3.14, then this is 2 pi, which is 6.28. So, in general, the radian measure of a central angle theta is obtained by dividing the arc length S by r. So, for any arc length S, we could just divide by r, and we end up with theta, where theta is measured in radians. Because the units of measure for S and R are the same, it's whatever units you're using, this ratio doesn't have any units. So theta has no unit necessarily. It's just simply, we call it radians, and it's just a real number. So what that means then is that we can, when we talk about a circle, we're going to be thinking in terms of that circle being measured this way. We can say from 0 radians to halfway in the circle, that's pi radians. And that makes coming all the way back around 2 pi radians. So let's kind of figure out how to count this then. That means that halfway from 0 to pi is pi halves radians. And that means all the way to pi is pi radians. And so if I do another half more, then that makes 1 pi half, 2 pi halves, 3 pi halves radians. And that makes all 4 quadrantial angles, that represent 90 degrees, 180 degrees, and 270 degrees. But we're talking in terms of radians. So going further then about cutting those in half and recognizing what we end up with now. So if we do those and cut them in half, look at where we end up. Half of a half is a fourth, so this is pi fourths radians. That makes half 2 pi fourths radians. And then between pi halves and pi, that makes that 3 pi fourths radians. And I'm going to be expecting you to know how to count these out like this and know exactly where you are on a circle in terms of radians. So we're going to continue with the fourths. Pi then is 4 pi fourths. That makes this 5 pi fourths. And 3 pi halves is 6 pi fourths. So that makes this 7 pi fourths. And then 2 pi would be 8 fourths. 8 over 4 is 2, so 2 pi. Let's go to talking about that in thirds. And I think what I'll do is I'll just change the color of my pen in order to do that. So we're going to talk about breaking things up into thirds. If I go 1/3 of the way from 0 to pi, then this is going to be pi thirds. And And so if I go another third, then I end up about over here, and then that's going to be that, since that first one is pi thirds, then this is 2 pi thirds. And then another third would be 3 thirds, so that's just pi, 3 pi thirds right there. So if we keep going though, and we end up over here, well, this is 4 pi thirds. And do one more, we got 5 pi thirds. And one more makes 6 thirds. So 6 thirds is 2, and that's 6 pi thirds is then 2 pi. Let's change the color one more time. And we're going to go for half of a third. Half of a third then is 1/6. So we're going to call this 1/6. So pi over 6. 2 pi 6 reduces to 1/3. 3 pi 6 reduces to 1/2. 4 pi 6 gives me 2 pi thirds. And so one more then, this is 5 pi 6. 5 pi 6. And then there's pi, which is 6 pi 6. So that makes this one then 7 pi 6. 8 pi 6 is 4 pi thirds. 9 pi 6 becomes 3 pi halves. 10 pi 6 becomes 5 pi thirds. And then this last one here is 11 pi 6. So those are the main divisions of angles that we're going to be showing you and talking about this most of the time in radians. And so get used to this picture and being able to find all of those measures. Notice that pi sixth is 1/6 of 180 degrees, so that's 30 degrees. Pi thirds is 1/3 of 180, so that's 60 degrees. And so we're going to start to see some relationships to some pretty nice measures as we go there. All right, so that brings us to then this idea of finding angles. If we're talking about now the complement, so remember complement was talking about adding to 90 degrees, which is pi halves. So we're saying pi halves then is equal to, and they're saying what is the complement of theta when it's equal to pi twelfths. So pi twelfths, well, added to what? I need the complement then of pi twelfths. Well, what am I really saying? Aren't I asking for 6 pi twelfths is 90 degrees? And so I need pi twelfths plus 5 pi twelfths gives me 6 pi twelfths. And so that means that 5 pi twelfths is the complementary angle to 1 pi twelfth. And so B says the supplement, remember, is 180 degrees, is going to be 180 degrees, and so that's a full pi, or 6 pi sixths. So the supplement of 5 pi 6 would be 1 pi 6. So we're saying we want the supplement being pi, adding to pi, and we're saying 5 pi 6 plus something is going to be 6 pi 6. So we just need 1 pi more, 1 pi 6, and there we have it. That is the supplement. That's the supplementary angle. And then an angle that is coterminal to 17 pi 6. Okay, 17 pi 6. Well, 6 almost goes 3 full times into 17 because 3 times 6 is 18. So 17 pi 6 would really be 3 pi plus 1 more sixth, right? So 17 pi sixths is basically this. It's 1, 1, 2, and then 3 is 1 more, and then back up 1. So there that is. So they're saying, what is coterminal to that? Well, isn't that 5 pi 6? So isn't that 5 pi 6? Isn't that also, if I'm going the other direction and trying to get to there, I'm starting here and I'm coming around this way, I could also call that negative 7 pi 6. And those are coterminal to 17 pi 6. All right, and let's take a look at some of these pictures to show us what we're really saying here. So in the first one, we're saying pi 12ths, the complement of pi 12ths. And so here is showing that I need the 5 pi 12ths in order to make 6 pi 12ths, which is pi halves. And so pi 12ths, the complement then is 5 pi 12ths. For this one here, we're talking about 5 pi 6 and going supplementary. So if we talk about supplementary, we're talking about, half the circle. And so to get that half circle completed when we have 5 pi 6, we need another pi 6. And so pi 6 then is supplementary to 5 pi 6. And so that makes pi 6 a supplement of 5 pi 6 and 5 pi 6 a supplement to pi 6. And then here's that one about the coterminal. So notice what's going on here. We're actually doing this travel from here. We're going half is pi, another half is another pi. So there's 2 pi. We made the full circle. But we want a little bit more, but less by 1/6. And so there we are. There's 17 pi 6. And so, but notice that that's the same as saying 5 pi 6 as far as just a coterminal measure. And then this is the one that I added a little while ago. If I went this way, I could also say that I went negative 7 pi 6. So here's example 4, converting from degrees to radians. Okay, so now we're talking about unit conversion of degrees to radians. So if we talk about a circle and recognize if we're just drawing a regular circle, that as we go from 0 degrees to 180 degrees, that's the equivalent of saying that I'm going 0 radians to pi radians. So there's pi, and it's the same distance as 180. So as I'm talking about degrees to radians, then aren't I talking about that there are 180 degrees in every pi? So that's basically saying 1 right there, and that's our unit converter of degrees to radians. So we've already kind of talked about the idea that there are pi radians in 180 degrees. That also means then that there are 180 degrees in pi radians. So we could use these as unit converters, and let's work how to do that now. So 135, they want us to take that and convert it from 135 degrees and say, what is that in radians? So we just use the unit converter and degrees down. That way that the degrees end up canceling as a unit, and we end up with pi radians on top. So as we do that, I want you to notice that 35 is actually 4 times 3 times 45, and that 180 is 4 times 45. So you'll see then that 45 cancels. There's pi on top, and we ended up converting 135 degrees to become 3 pi fourths. So there that is. So 540, I want you to know that, by the way, that 180 times 3 is 540. So we'll just kind of keep that in our minds. But we start off with 540 degrees. And we multiply that by pi over 180 because we're going to expect degrees to go away. So degrees are going to cancel now, and 540 over 180 is 3, and so this ends up being 3 pi. Okay, and finally, we have negative 270 degrees. If you need to, you could draw like a unit circle and just kind of come up with what that looks like. Negative 270 degrees. Well, let's see. I'm going to be going from here and heading in the negative direction, and then heading over here a little bit more, and that's negative 270. So what is negative 270? Well, Let's go ahead and convert that first. We're going to convert that to, and we'll do pi over 180 again, because that way degrees cancel. And 270, well, that's 90 degrees times 3. We'll say negative 3 times 90, and 180 is 2 times 90. So 90s cancel, and I end up with 3 pi halves, and it's negative. So that's negative 3 pi halves is 270. But notice also, and we can say it this way because it's coterminal with 90 degrees, we can say that that's pi halves as well. So we could state it either way. It's negative 3 pi halves or pi halves radians. And there's our answers right there. So that's converting degrees to radians. But what if we want to convert radians to degrees? So if someone gave us negative pi halves radians, you could just do it this way visually and say, okay, you're just talking about this distance right here, negative pi halves radians, and call that negative 90 degrees. Or we could just do that too with the converter. We can say negative pi over 2 radians. We want to multiply that by a unit converter. We want to get rid of pi, and we want to introduce degrees. So look at what we end up with. 180 over 2 is 90. That's a negative. Pi cancels pi, and we're at negative 90 degrees. So there's converting from radians to degrees that way. So let's do it again. We have 9 pi over 2, and we want to convert that. So pi is going to go down this time, and that means that 180 is going to go up on top again. And we have 180 divide by 2, and we're going to get 90. And so 9 times 90, and pi cancels pi, and that's degrees. So 9 times 90, 9 times 9 is 81, so that's 810 degrees. And then lastly, we have 2 radians. 2 radians. Well, we don't have pi there, but we know that we have to divide by pi and multiply by 180 degrees. So that's going to be 360 degrees over pi. 360 over pi degrees is really how we would say that. So let's talk about finding arc lengths. And here we're given an arc length. We're asked for how far is it from the beginning at the positive x-axis. If we go around 240 degrees, how far is that if the radius is 4? Well, it starts with that we know that the circumference of the circle has a formula, and it's 2 pi times r. Well, r is 4 inches, so we're saying that the circumference then is going to be 2 times 4, which is 8 pi inches. So that's how far around the entire circle is 8 pi inches. Well, we're also saying that we know that there are 240 degrees in the desired part of the arc, but that's out of the whole circle, which is 360 degrees. So that's really a ratio then, and we could just take how far around the circle and multiply that by the ratio, 240 over 360. So 240 over 360, we can actually cancel the zeros. I can divide 24 by 6 and 36 by 6 and get 4/6, which really becomes 2/3 times 8 pi, which really becomes 16, or we could say it's 16 pi thirds, and that's the length of the arc in radians. So this brings us to a topic called linear and angular speed. So I like to compare this to or liken it to riding a bicycle. So if you had a bicycle and here's a bicycle wheel, very typically on your bicycle wheel you have like a little stem for your air, and there's a very simple bicycle wheel. So think about this. What's going on is that the bicycle wheel, and think about that stem going around and around and around. So every time that stem goes around, that's one full revolution of the wheel. And so aren't you traveling a linear distance of, you know, 2 pi times the radius of the wheel, and that gives you how far you are going in a linear distance. So think about what that's saying. That the linear speed then, consider a particle moving at a constant speed along a circular arc of radius r. If s is the length of the arc traveled in time, then the linear speed of the particle is the arc length, s, over time, t. And so that's how you talk about that. So moreover, if theta is the angle in radian measure corresponding to the arc length s, then the angular speed of the particle is, angular speed is equal to central angle divided by time, or theta over time. That's the angular speed. So we're talking about two different things, linear speed and angular speed. So there we have it. I think I'll stop right there and let's talk about what the homework is. You've got section 6.21, and what we've done is come up with 24 problems on page 461, problems 1 through 15 odd, and 28 through 85 every other odd. So go ahead and do those. If you need help with them, come in during after school or study hall, and I'll help you. Have a good weekend.